This page continues our discussion on thermal noise, looking at the very practical challenges it creates, especially when we want to build high-resolution ADCs. The main takeaway is that for ADCs with a resolution higher than about 10 bits, it becomes very costly to make the thermal noise smaller than the quantization noise. And when we say costly, we're talking about three critical resources in chip design: power, area, and speed. You often have to sacrifice one to improve the others. Let's look at the concrete example given here to make this clear. Imagine we're designing an 11-bit ADC with a full-scale input voltage of 1 volt. We can calculate the power of the inherent quantization noise, Q understood. The calculation shows this comes out to be the square of 141 microvolts RMS. This value itself isn't the key part. What's important is that this is our noise budget. For the ADC to perform like a true 11-bit converter, any other noise sources, like thermal noise, must be significantly smaller than this quantization noise. So what happens if they're not smaller? The next point says that if our thermal noise power, N_T, is the same as our quantization noise power, Q_, the total noise power doubles. In electronics, when power doubles, we say there's a 3 decibel or 3 dB increase. This means our signal-to-noise ratio, or SNR, takes a 3 dB hit. It gets 3 dB worse, which is a very significant drop in performance. It's like losing half a bit of resolution. To avoid this, a common design goal is to keep the impact on SNR minimal, say, less than 1 dB. To achieve that, the thermal noise power must be much smaller than the quantization noise power. A good rule of thumb, as shown here, is to make the thermal noise power at least 10 times smaller than the quantization noise power. Now, here comes the really critical part. How do we make the thermal noise smaller? As we saw on the previous page, the thermal noise from switches is related to kT/C. To decrease the noise, we have to increase the capacitance, C. So, to meet that less than 1 dB hit requirement for our 11-bit system, we'd need a sampling capacitor of 2 picofarads, PF. This is where the problem starts to scale badly. If we want just one more bit of resolution, a 12-bit system, the quantization noise becomes 4 times smaller. This means we need a capacitor that's 4 times larger to keep the thermal noise in check. That's why the value jumps from 2 picofarads to 8 picofarads. 4 on-chip capacitors, 8 picofarads is already quite large. Now, let's push it even further. What about a 16-bit system? If you follow the scaling, the required capacitor size explodes to 2 nanofarads NF. A 2 nanofarads capacitor is enormous for an integrated circuit. It would take up a huge amount of expensive silicon area and would be very slow to charge and discharge, limiting the speed of our ADC. That's why the slide says it's almost physically unrealizable on chip. This is the fundamental reason why designing very high-resolution, high-speed ADCs is so challenging. It's a battle against the physics of thermal noise.